Hi, I'm Lauren White. In this lesson, we'll talk together about how to predict if an SN2 mechanism is actually going to happen based on the steric hindrance. All right, let's think about what role steric hindrance plays in SN2 reactions. So first, remember that SN2 reactions occur in one big step. The nucleophile attacks the electrophile. There's a transition state where the electrophile is kind of hanging on to the leaving group and the nucleophile, and then the leaving group is kicked off. Well, in this case, our nucleophile has to be able to get close enough to the electrophile to actually attack it. So we want our electrophile to have a lot of bulky groups around it. Well, no, we need our electrophile to have as little steric hindrance as possible. So what this translates to is the best electrophiles for SN2 reactions are methyl and primary. Secondary and tertiary electrophiles, however, generally won't react at all through an SN2 mechanism. There's just too much stuff in the way for the nucleophile to get into attack position. Let's do some examples. Let's start with A. First, let's figure out where our electrophilic carbon is in these molecules. So in both cases, the carbon that is bound to the electronegative atom will be feeling a little positive. So in the molecule on the left, our electrophilic carbon is right there, and in the molecule on the right, our electrophilic carbon is right there. Now, in the molecule on the left, we need to think about how many other carbons there are. We see that our electrophilic carbon is bound to 1, 2, 3 other carbons, and so this is a tertiary electrophile. In our molecule on the right, though, we're bound to just one other carbon, so this is a primary electrophile. Well, which one's going to be better for an SN2 reaction? You guessed it, the one on the right, since it's a primary electrophile. All right, let's try B. Here, notice that cyanide, this CN group, that's our leaving group in both cases. So we need to figure out which carbon is going to act as our electrophile here. Well, it's the next carbon in line, here and here. Let's see how many other carbons are attached. In the molecule on the left, aside from the carbon in our leaving group, we're attached to just this one other carbon, and then the rest of the chain. The same is true for the molecule on the right. Just this one other carbon. So both of these are primary electrophiles. And you may have deduced at this point, these would be equally likely to react in an SN2 mechanism since they have the same amount of steric hindrance. Okay, one more. Let's look at C. In the molecule on the left, our electrophilic carbon is right here in the middle, attached to that electronegative iodine. And this electrophilic carbon has two other carbons attached to it, one on the left and a second one on the right. So this is a secondary electrophile. What about the molecule on the right then? Well, the electrophilic carbon must be the only carbon, and iodine is a far better leaving group than fluorine. So if this were to go through an SN2 mechanism, our iodine would leave, and our electrophile would be left bound to these two fluorines, one on its left and a second one on its right. Now, you might be wondering, well, how do I know whether being bound to two other carbons or two fluorines is better for an SN2 reaction? Well, let's think about what these two carbons on the molecule on the left also have on them. Remember, these aren't just bare carbons. They also have 3 hydrogens each. So what this molecule really looks like is a carbon with 3 hydrogens, carbon over here with 3 hydrogens. That takes up quite a bit of space. The molecule on the right, though, just has the 2 fluorines. And remember, fluorines are a little smaller than carbon anyway, and they also don't have those 6 other hydrogens. Thus, this molecule on the right has less steric hindrance and would be more favorable for an SN2 reaction. Now, you should feel more comfortable predicting whether an SN2 mechanism will occur based on the steric hindrance.